are continuous at every x value in their domains. The first type of functions that are continuous at every x value in their domains are polynomial functions. So an example of a polynomial function might be f of x is equal to 3x to the 7th minus 5x squared plus 4. Okay, so polynomials are x's raised to whole number powers, made with some coefficients in the front, and then added and subtracted together. So every polynomial, and by the way, the domain for any polynomial that you write down is all real numbers. And so every single polynomial that you ever write down is a function that is a continuous function on the interval from negative infinity up to positive infinity. All right, now the second type of function that is continuous at every x value in its domain are rational functions. So, for example, I might have a function g of x is equal to x squared plus 4x plus 3 divided by x squared minus 9. Now, at this point, you might be saying to yourself, wait a second, time out, Ben, time out. You just told me your theorem says that these functions are continuous at every x value, and take a look down here, we've got an x squared minus 9 in the denominator, so certainly we're probably going to have either wholes or vertical asymptotes when x is equal to plus and minus 3. And the key here is that this in their domains, that's crucial here, because for this rational function here, we're not talking about x being plus and minus 3. So this rational function is continuous for every x value except for x equal to plus and minus 3. The third type of function is root functions, which are things such as maybe k of x is equal to 2 times the square root of x plus 3 times the cubed root of x. So anytime you have roots in your functions. And again, because we have domain issues here, this is only for x values that are greater than or equal to 0. And last but not least, number 4 is trig functions. So trig functions are all continuous on their domains. So remember those vertical asymptotes on tangent? Those x values are not part of tangent's domain, so we don't count that. But a trig function might be h of x is equal to 5 times the sine of 100x. And the sine function, its domain is all real numbers, so 5 times the sine of 100x is continuous for all real numbers. All right, so this theorem, again, doesn't sound that cool, but here's why this becomes useful. Okay, there's a corollary to this theorem. Now, what's a corollary? A corollary is a cool afterthought that you get after a major theorem. And the corollary says that when dealing with a function that is continuous at x equal to a, we can plug in a and work with our limit. So, for example, if I have the limit as x approaches 1 of x to the third minus 2x plus 52, then what I see here, and solve that over x minus 3, then what this says is that if I want to calculate this limit, what I see here is a rational function. And my rational function, the domain, is all x values except for x equal to 3. And so as I'm thinking about this function, x cannot be equal to 3, but we're not looking at x value equal to 3. Okay, so when x is equal to 1, the limit of this function as x approaches 1 is going to be exactly equal to the function value when x is equal to 1. So by this theorem over here, we're looking at a rational function where 1 is not part of our 1 is part of our domain, which means we can immediately plug in x equal to 1 into this function. No factoring, no nothing. Okay, so this limit is equal to 1 to the third minus 2 times 1 plus 52 over 1 minus 3. So in our numerator we have 51, and in our denominator we have 2. So as long as we don't get a 0 in the denominator when we have a rational function, as long as we don't get a 0 in the denominator from the x value we're approaching, we can just plug that x value into the top and the bottom and it calculates our limit for us. All right, so that's kind of helpful.
Some negatives.